Okay. So now we're going to look at the middle possibility of bonding. Say, what do you mean the middle possibility? Well, we have two extremes. One extreme, ionic. One atom gives its electrons to the other. Okay? That's one extreme, give and take. The other extreme is sharing. Sharing everything evenly. Okay? Today we're going to talk about sharing that's not even. They're sharing, but they're not doing it evenly. Okay? And that leads to a polar bond. So we're going to talk about polar bonds and polar molecules over the next couple of days. Okay? So a polar bond is not this. Okay? This is one of the extremes. This is where they're shared evenly. If I put together two Fs, those Fs both want those electrons equal amounts. So they're going to pull on each other's electrons just as hard as they pull on their own, and everybody's going to share perfectly. You have two of the same atoms, they're going to share perfectly because they're pulling equally hard on the electrons. This is a bond where both ends are the same. That is non-polar. Polar means you got ends that are different. And here on my bond, if they're the same atom, they're going to be pulling the same. So one end won't be different, both ends are going to be the same. So it doesn't have ends that are different, it is non-polar. Think about the place where you see poles used. North Pole and South Pole, the ends of the Earth, top where the axis goes through. Or magnetic North and magnetic South Pole, which way your magnet points. On a battery, those two posts that come out can be referred to as poles. Positive pole and a negative pole. And polar means opposite ends. Okay? When two different atoms are connected, the electrons may not be shared evenly. One of those electrons may pull harder, one of those atoms may pull harder on electrons than the other. And if one pulls harder than the other, they're not going to be shared evenly. So when the electrons are not shared evenly, that's when it's a polar bond, a polar covalent bond. Say, what do you mean by not shared evenly? Well, I had a little brother. I did this to him. Hey, let's pull our money and share this. I'll keep it in my room. That's shared unevenly, right? Why could I get away with it? Because I could pull harder than he could. I was bigger than he was, a little brother. Yeah? Okay, so what we need to remember is that we've already talked about how hard atoms pull on their electrons. That was one of our topics last semester. Anybody remember what we called it, measuring how hard it pulled on its neighbor's electrons? One word to describe that. That word was electronegativity. Electronegativity. That was one of our topic words last year. How hard you pull on your neighbor's electrons. And this was our definition. Way back in chapter 6. All we did with electronegativity in the past was look for patterns in how hard they pulled. Patterns on the periodic table. And the patterns we saw were that as I went across the periodic table, electronegativity went up because more protons could pull harder on the electrons. More positive pieces pulled harder. As I went down a group, the electronegativity went down because there were more layers of electrons between the nucleus and the outside. That's all we did with it back in chapter 6. We saw it as a periodic trend. Now we need to use that periodic trend to explain chemical behavior. Okay? You don't have to memorize these numbers. I'll always give you an electronegativity table. Okay? But the numbers vary. The most electronegative is fluorine at 4. The least electronegative on this one is cesium at 0.7. Okay? But here's the thing. My analogy for electronegativity was greed. Okay? So if you put a greedy person alone on a desert island with cameras watching, could you tell just by watching whether they were greedy or not?
Well, he's alone.
He's alone. Could you tell whether he's greedy?
No.
No, there's no way, right?
There ain't nobody to share with.
Nobody to share with. If you had somebody on a desert island that was alone and they were the most giving person in the world, could you tell? Oh. Okay, if I put 2 greedy people on the island, 2 equally greedy people, how would the stuff get divided? Would one of them have more than the other?
The one who's bigger.
No, because they equally pull hard. So they're equally greedy. They get equal pull on those things. If I put 2 equally greedy people on the island, everything's going to be evenly shared. Because if somebody has too much, the other one's going to let them know and say they got to give it. Right? If I put 2 selfless people on a desert island, everything's going to be evenly shared. Because if I've got too much, I'm going to give it away. If I got more than you, you get the extra. Right? So 2 greedy people, 2 selfless people look identical as long as you're not listening to the conversations. Right? So you couldn't tell a difference. And that means they're going to share evenly. 2 atoms of the same kind share evenly, no matter how greedy they are. 2 fluorines hooking to each other. They're going to pull like 2 greedy people. They're going to share those electrons evenly. Something with a low electronegativity. 2 lithiums. Put 2 lithiums together. They're going to share perfectly because they're both trying to give their electron to the other one. Take my electron, please. Okay? So where you're going to see a difference is if you put a greedy person and a selfless person on the island. Are they going to end up sharing evenly? No. So the selfless person is going to have less. That's why I call it selfless, because you yourself have less. But no, that's not why they call it that. So it's not how big the numbers are. It's how different the numbers are that gives you a difference. So what we need is the electronegativity difference, how different the 2 are. Because if they're the same, they're going to share evenly. If they're different, they're going to share unevenly. So, difference is a math word. What math operation gives you the difference? Subtraction. So I look up the 2 numbers and subtract them. Don't care what order, it's absolute value. I want to find out how far apart they are. And use this table I got off, this is table 6.2 off page 177 back in chapter 6. You don't have to memorize it. I'll print it on the test. Okay? So how different is different enough? If you do the subtraction and get a difference of a 0.4 or less, we're going to say that those 2 atoms are pulling close enough to the same amount that they're going to share evenly. May not be perfectly even, but it's going to be hard to notice that it's uneven because it's got a tiny difference between. And if they do 2 of the same atom, fluorine's 4, second fluorine's 4, subtract 4 minus 4, I get 0. It's going to share perfectly. Okay. As that difference gets bigger, one atom is going to be pulling the electrons more than the other. And just like me and my little brother, it would be in the situation if we're going to share that, I'll keep it in my room. Right? So that gives me If I get to 0.5 to 1, I get a little bit polar. 1 to 2, more polar. So really, anything from 0.5 to 2, do that difference, subtract that difference. Anything between 0.5 and 2 is polar. Just the bigger the number, the more polar it is. That's why they did this. Well, they did this just to say you can be a little bit polar or you can be more polar. But what happens if you get a difference bigger than 2? That means one is pulling really hard and the other one's not pulling back. What happens when one pulls really hard and the other one doesn't pull back? But they take it, right? So if the difference is bigger than 2, it's ionic. Because how are you going to have a difference bigger than 2? You'll have something over here, a metal, with something over here, a nonmetal. Something with a low number and something with a high number. You subtract those two, you're going to get a big number. So it's just a different way of looking at metal, nonmetal. It's about how hard is that atom pulling on electrons. Okay, so what we're saying is, even if we're saying the ionic, they are sharing a little bit. They share for a fraction of the time. So to make a bond polar, I look up electronegativities. See if a bond's polar. I look up electronegativities, subtract those two, and if whatever the answer is, that'll tell me what it is. Less than 0.4 or less, it's nonpolar. 2 or bigger than 2, it's ionic. In between, it's polar. There's our extremes. Sharing perfectly, 0. Giving and taking, bigger than 2. And polar is in the middle, sharing unevenly. Okay, so we're going to have to let people know that they're polar. Okay? And I can't just label a plus or a minus because it's not a whole charge. It's only a partial charge. It only partially takes it away. So it's not a whole charge, it's a partial charge. So somehow we have to write partial. And the way scientists write the word partial is with a letter of the Greek alphabet. You know you're going to learn the Greek alphabet this year, but it's like the 5th time it's shown up. And this symbol right here is a lowercase delta. It looks like an S that you bring the tail up on, so make an S and then just bring it all the way around. Eventually that straightened out and we turned it into our lowercase d. So over time it became our lowercase d. Started off as a lowercase delta. So make an S to bring that tail up and around. Capital delta is a triangle. Lowercase delta, this. Okay? And that symbol means partial. So delta plus means partially positive. Delta minus means partially negative. And you're going to have both. You can't have partial positive without having partial negative. Because to get partial negative, you had to pull on electrons. That means you left a partial positive behind because you pulled those electrons away from something else. Okay, so here I have labeled this bond with a partial positive and partial negative. How did I know which one was positive and which one was negative? Well, the table. I looked them up on the table, and hydrogen was 2.1, and chlorine was 3.0. 3.0 minus 2.1 is 0.9. And the hydrogen's got the bigger number. So the 0.9 tells me, oh sorry, it's over here, that it's polar. 0.9 tells me it's polar. And the Cl is negative because it had the bigger electronegativity. It was 3.1. The one with the bigger electronegativity pulls harder, so the electrons are going to end up near it. I mean, if you were looking for the thing my brother and I shared, you'd start off in my room because much better chance for it to be there. Okay. Down at the bottom, I've drawn the second way to do it. There's two ways to do it. And the second way to do it involves this arrow. So here's what I got, H and Cl. And then I looked it up and saw that Cl had the bigger number. So the electrons were being pulled towards the Cl. So the arrow showing which way they move. And when you take electrons away from something, if you cross that, it looks like a positive sign. So the electrons move towards the Cl. It's got a positive sign. Another way of thinking of that is the electrons are going to spend more time near the Cl. And whether something's polar or not has a big effect on its behavior.
Right there.
They hung up on me. Yes, they didn't want to talk to me. Whether something's polar or not has a big effect on its behavior. You have to shake up your salad dressing because water's polar and oil's not. Okay? So one of the big things about how something behaves, once you determine that it's molecular, decide whether it's polar or not. So ionic, if you chemists first decide between ionic and molecular, usually by see if it conducts electricity. Once they've done that, once they decide it's molecular, then they want to see whether it's polar or not. Because polar affects lots of behavior. And polar bonds lead to polar molecules. So instead of just the bond having an end, the molecules have an end. Yeah. So a polar molecule is going to be like a polar bond. A polar bond was where you had a positive end and a negative end. A polar molecule, so we have a positive end and a negative end, but not on just the bond, the whole molecule. Okay. So polar means ends. We put on a bond, it's a bond with a positive and negative end. I put on a molecule, it's a molecule with a positive and negative end. Okay. If a molecule is going to be polar, it has to meet two conditions. If it doesn't have both of these conditions, it can't be polar. Condition number one, it has to have polar bonds. So the first thing I do, this is what I check first because this is easy. I look up some numbers on the table and I subtract them. So first I look to see if it has any polar bonds. If it doesn't have any polar bonds, I'm done. If it has polar bonds, I got to go check condition number 2. So first thing I check, once I write the structural formula so I can see what's bonded together, I look up the difference and look at every bond. So I'd say, is this bond polar? And I look up the number for nitrogen, the number for hydrogen, see if it's polar. And these are all the same. If there's been an O, I look up nitrogen and oxygen. Every kind of bond, I want to see if there's any kind of polar bond in there. If it has a polar bond, I move on to step 2. And step 2 is about symmetry. I can't have positive or negative ends if everything is evenly spread. Symmetry is the opposite of polar. Polar means you have ends that are the same. Symmetry means polar means you have two ends that are different. Symmetry means all the way around it's the same. symmetrical, mirror images. Okay. But instead of just mirror images, in 3D, all the way evenly, so like one spot is the middle of all this. It's got a center. That's really the center. So how can I determine if it's symmetrical? I got to figure out the shape. So the reason why we figured out shape was so we could figure out if it was symmetrical, so we could figure out if it was polar. And you'll read about that as you do Reading Guide 8.4 tonight. Okay. And I will see you tomorrow. And we'll see if molecules are polar.